Hello and welcome. In this tutorial we will explain how to do a PID control with Arduino Opta. For this we will be working with a system that consists of a water tank. We will have an entrance of water whose opening we can control from 0 to 100%. We will have a way to continuously measure the height of the tank, meaning for each individual height we will have a reading. And finally we will have an outlet which will be constant, so it will not be controlled. It will be just an opening with a certain area, but it will be uncontrolled. In this video we will touch on the following points. If you want to skip some of them, just see the description and I will have time codes for each. First, we will see the physical construction and architecture of the system. Then we will talk about the physical model of this phenomenon and how to establish the equilibrium point. Then I will very briefly touch on the basic idea of PID control. Next, I will program a simple interface for using the systems, just a couple of buttons. Then we will do the proportional control programming, so the P out of the PID, and testing. And finally, I will do the integral control programming and testing. For the physical construction and architecture of the system. So the system will work as shown on this drawing. We will have a tank. The outlet of the tank will be a valve with a certain opening that will never be touched again, so meaning it will just be set in a certain position and we will forget it. We just must know that at the bottom of the tank there is an exit for water. Then we will have a device to measure the height of the tank. The height will be between 0 and 3 meters, and accordingly the signal that we will receive from this sensor will be from 0 to 10 volts. And finally we have a place that we can control, which is the valve to fill the tank. Again, the opening of this valve, we can command it between 0 and 10 volts, and depending on the value it will be more or less open. Now, to build this system we could do what's shown in the picture, a direct connection, where we can read directly from the level meter, which we could connect to the Opta, and then we would be able to also send a voltage between 0 and 10 from the Opta to control the fill valve. However, the basic module of the Opta, well, it can read because it has an analog read, so the reading part it could be done, but for the output it's just a solenoid, so it's either 0 or 10. You can send 5.7 volts. So this way will not work unless you have an expansion module, in which case you can do it like this, no problem. So instead, what we're going to do is what's shown in this picture, where we can imagine that we have a lab, and in orange I've represented a PLC which is capable of reading and writing analog values. So we connect the level meter to this PLC, and we connect the fill valve actuator, rather the signal, also to this PLC. And then we interact with this PLC in the lab through Ethernet Modbus. So for that I've done a couple of videos telling how to do this. In practice it's very similar to working normally with the Opta. It's just variables created elsewhere that you can then relay in real time. I want to briefly touch on the physical model of this situation. So first of all, we're going to be working around an equilibrium point. An equilibrium point can be defined as a condition, a situation where we have the same inflow as outflow of water, and so the level remains constant. For example, here I've shown in this picture, we can imagine a situation where we have the tank half filled, and then through the inflow, because we have regulated the valve, it's set at 0.5 liters per minute, and then the outflow is also 0.5. This is just physics. It's not because we have regulated it, but simply because depending on the height of the tank and the section area of the outlet, the outflow will be automatically established. If the tank is very high, at the bottom of the tank, the outflow will be higher, and if the level of the tank is very low, then the outflow will naturally be less because there is less pressure at the exit. In any case, we're going to be working around an equilibrium point, and we will take it from there. So, for example, if we start from this last situation and then we decide that we want a 60% level, so what would we do then? Then we would increase the inflow, and in this way the water level would raise, simply because we are putting in more water than is exiting at this point. But the outflow is unknown. Well, it can be calculated, but what I mean to say is that it's uncontrolled. So what we would do is we would increase the inflow and then the tank would raise, but maybe the outflow will be higher or lower than 0.6. I don't know. We don't know. If we keep adjusting the system, we will reach a point where we will have a 60% level as we wished, and then there will be a value of inflow which is dictated in fact by the outflow at this height. The height influences the outflow, and then the inflow must adapt to this outflow in order to establish an equilibrium point. This is why the equilibrium point is not constant. You cannot just say that a certain inflow guarantees that the level will not move. The equilibrium point, rather the equilibrium inflow, depends on the tank height. So what we will do is that we will adjust the PID around an equilibrium point, which at first can be located where we want. We must know that the system will work very well near the equilibrium point, but it will work less well far from the equilibrium point, because this change in the exit speed of the fluid caused by the different height is not taken into consideration with the linear model. So what we're going to do is we are going to take the middle of the tank as the equilibrium point, and then we know that if we work around the middle it will be very good, and then if we want to set a tank level which is very high or very low, the system will have a harder time setting it. Again, I just want to point out that the equilibrium point has nothing to do with PID control. It's just a physical situation where inflow is equal to outflow. The first thing that we are going to do is to find out this equilibrium point. So for this, we must take into consideration again that the exit speed will depend on the tank height. So we are gonna fill the tank to about half the height, and then we are gonna be seeing what's the configuration for the inlet that more or less keeps the system such that the inflow is equal to the outflow. Okay, so here let me briefly present the system that we will be controlling. It is a water tank that has a couple of actuators. So first, it has a fill valve here that we can open, and then if we open it, an inflow of water is allowed to enter, and we can close it. As I mentioned, it's controlled between 0 and 10 volts. Then we have here an outlet valve, so if we open it, then there is a discharge and the level is reduced. And finally, the level at each moment is controlled through a level meter, which gives us at each time the reading. For our PID, the fill valve is what we will control, the level meter we will read constantly, and the discharge valve will be untouched. So we will just establish a value. So for example, we will set it at I don't know, 2 volts. Okay, 2.2 volts, for example. And that's it. So now what we are going to do is to try to find the equilibrium point where the water level is stable in the middle of the tank. Okay, so we have left the discharge valve fixed and we have adjusted only the inlet valve to find a value around which the water level is constant. So what we're going to work with is that a value of 2.3 volts at the entrance valve will lead to an equilibrium situation at about 1.63 meters. So in this situation, the inlet flow is equal to the outlet flow and the height is set at this value. Okay, so now in order to start with the PID programming, I first want to touch briefly on certain concepts. Our target variable will be the reservoir water height. So that's the variable that we will be controlling. We will say, I want the water to be at 1.35 meters, for example. And for that, we will act through the inlet valve opening. We can control that at any moment at will. And finally, we will also be needing, obviously, the reading of the height at each moment in order to know our situation to act accordingly. First, the first concept that I want to introduce is target level and error. So for example, in this picture, what we have drawn is a situation where we have a current water level, which seems to be around 60%. So our sensor will tell us 6 volts. And we wish to have the tank at 80% height. So we want to have 8 volts. Now the error is the difference between the target and the current. So in this case, it will be 8 minus 6. So the error will be plus 2 volts. In this other situation, we can imagine that we are in the same starting point, but actually what we want is to have the water tank level at 20%, but we have it at 60%. So in this situation, the error will be 2 minus 6 equals minus 4 volts. With the concept of error clarified, we can talk about the proportional action of the PID. So what we are going to actually set on the valve, which I have called here output, is equal to the equilibrium output plus the proportional action output. The equilibrium output is the output that is necessary to maintain the equilibrium point. That's already set and is permanent once we have established it. And now let's imagine, for example, that at equilibrium, the inlet valve signal was 2 volts. So the equilibrium output is always 2 volts. And then we add or subtract a certain proportional action. In this example, let's say that we want to set 80% and we have 60%. We calculate the error, and that's 8 minus 6, so that's 2 volts. The units are not important. We can talk about in percent, volt, or whatever unit. It's not, that's not important. So in this case, the error is 2 volts. And the proportional action will be a constant, which is a K prop, multiplied by the error. If we imagine that we set the constant at 0.1, then the proportional action will be 0.1, which is the K, multiplied by the error in this instant, which is 2 volts, equal 0.2 volts. So in this moment, the exit value, the value on the valve will be 2, which was the equilibrium value, plus 0.2, which was the proportional action output. So in this case, what the system is trying to do, it is trying to elevate the equilibrium value into 2.2 so that the water rises. If we see this other example where we want to diminish it, again, we can do the same reasoning. So in this case, the target is 20%, but now we have 60%, so the error is -4. If we calculate the proportional action, 0.1, which is the same constant, multiplied by -4, which is the error, then the proportional action is -0.4 volts. So the value that we will send to the field valve, which remember was between 0 and 10, it will be the equilibrium output, which again has already been set since the beginning, so that's 2, minus 0.4, which is equal to 1.6 in this instant. So again, what we can see here is that the equilibrium value is diminished so that the inflow is lesser, and then the system hopefully descends. So that's how the proportional action works. Now we are going to enable the user to choose the value of the target height of the tank that he wants. For that, we are going to be putting a couple of buttons into input 3 and input 4. So in input 3, we will put a button such that if we press this button, the target height will increase by 10 centimeters. If we press the button in input 4, the target height should decrease in 10 centimeters. If you work out the math in this situation, you will see that in order to increase or decrease the target height by 10 centimeters, you have to add or subtract 33 from the variable that stores the target value, the target height. This is because the height is actually not stored in volts, but in centivolts. So that's not important, it's just that we have to either add or subtract 33 to do this operation. So to do that, the first thing that we need to do is we need to go in the menu to programmable inputs, and we need to declare a couple of variables, I3 and I4. And there we declare a couple of variables to assign to the reading of the push button. So we will have in input 3 a variable so that we know that the button has been pushed, and the same for input 4. Next, what we will do is go to global variables, and we will also declare a couple of variables, which are here in number 2 and number 3. Number 2 is target level centivolts. So in this variable, we will store the target level of the height of the reservoir. The difference between 2 and 3 is just the units. In the case number 2, we will store this height in centivolts. Remember that this is in relation to the reading to the height sensor, which is between 0 and 10 volts, so which is between 0 and 1000 centivolts, but it's the same. And we will have it in centivolts and in centimeters. Next, we will create a ladder diagram. In this diagram is where we will perform the operation of if the button is pushed, we add 33. In this case, see that the contact that I have squared in red is set to positive. This means that if the contact is detected changing from 0 to 1, then the positive will turn into, it will be enabled, and this action will be performed once. And these two actions are, the first one, if the button of plus 10, that was I3, if this button is pushed, then the value of target level will be increased by 33, and the result will be restored in target level. And the same for minus. So if the bottom minus is pushed, then the target will be decreased by 33, and the result will be stored in target level centivolts, same variable. Then I have created a functional block diagram, and this is just in order to cap the maximum and minimum value that target level can have. This is so that we don't have a target of -3 meters, for example. If you want to cap it between 0 and 3 meters, you need to put here 0, and here you would put 1000. I have just chosen to cap it at 2.3 meters, more or less, but you can put it however you want. And finally, again, in the functional block diagram, I have created this last function here, and what it does is it transforms. So it's just a multiplication. You take the target level in centivolts, you multiply by these constants, and you will get the target level in centimeters. So now let's see how this works. Okay, so now, as you can see on the image, we have installed a couple of buttons to increase and decrease the target level. And then we have also loaded this program into the Arduino, and we are tracking the variable values. We are tracking the target level in centivolts and in centimeters with the conversion that we mentioned earlier. So for example, if we press the button to increase, you can see that the target in centimeters has increased. Let's see, okay, here. So if you press again, we keep increasing in the increments of 10 centimeters, as the function shows. Then if we want to decrease, we just press the other button. And like that, that's how the user will be able to choose the target value that he wishes the water level to have. In this case, we wish to have 49 centimeters, which equals a signal, a red signal, a wished red signal on the water level meter of 165 centivolts. That's what we wish to read. What we actually read has nothing to do with what we wish, and that's the source of the error that we will try to correct with the PID control. Okay, so to sum this up, now we have set up this configuration where if we press this button, the target height will be increased, and if we press this, the target height will be decreased. So now the user can set the height, the target height, however he wants. Also, we know that the error is the target minus the real red value, and now we have established the target however we want. Next, we should, to finish this calculation of the error, we just need to read the sensor. So for example, if I have a target of 1.5 meters and I read 1 meter, then the error will be half a meter. In order to finish integrating the existing variables, this is the actual construction that we have. So now we have the Arduino connected to a switch, and the switch is also connected to a Modbus slave device. And in this slave device, we are gonna just use two registers. We have a register which stores the red value of the height, and we have a holding register where we can write the target value for the opening the filling valve. So we just need to manipulate these two registers to and from the Arduino Opta. We will read the height and we will write the value that we want on the filling valve.